Hello, welcome to this session. We're going to have a few talks on Hamiltonian simulation, or simulation of Hamiltonians and their properties. And this first talk is a merged talk, and it's going to be divided into two 15-minute talks with 5 minutes after each talk. And both of these first two talks are going to be about simulating sign problem pre-Hamiltonians using Monte Carlo methods. And our first speaker is Elizabeth Crosson from Caltech.
Thank you. So my talk today is going to be about comparing some optimization methods that are inspired by physics and how we can look at particular cost functions to prove things about separations in the performance of these various optimization algorithms. This is joint work with Aram Harrow, and we also presented it at Fox last year. And if you want to see an extended version of my talk, you can search the title on YouTube, and you'll find a 40-minute version from last year's Adiabatic Quantum Computing Conference. So we're going to think of optimization as the task of minimizing a real-valued function on the domain of n-bit strings. And we're going to take some inspiration from physics and look at systems that obey some minimization principle and try to harness the dynamics of those systems to build better optimization algorithms. Of course, a famous example of this is classical simulated annealing. So this is a Markov chain Monte Carlo algorithm that simulates thermal cooling by attempting to sample a Gibbs distribution with an energy given by our cost function f at some schedule of temperatures starting at very high temperature and cooling down to low temperature. So the most important question for us here in this room is, can quantum mechanics inspire faster optimization methods? So some intuition for why this might be the case is that thermal excitations give us one way to explore the domain of our cost function, but quantum dynamics allow for new kinds of ways to explore this domain. And so maybe just on a very intuitive level, quantum dynamics might allow us to tunnel through tall, narrow barriers that would take a long time to climb over thermally. Okay, so some theory to back this up is that quantum annealing can be exponentially faster than classical simulated annealing for particular cost functions with tall, narrow energy barriers. So this idea has a long history, starting with Farhi, Goldstone, and Gutman in 2002, and then it was extended by Reichard in 2004, and more recently there's kind of been a renewed interest in these sort of problems as we get closer and closer to building real-world quantum annealing hardware. Okay, so let me just cover the basic idea of adiabatic optimization. You want to, again, minimize this function f. So what you're going to do is you're going to write down a Hamiltonian that's diagonal in the computational basis that has the values of f listed along the diagonal. And then you initialize the qubits in the ground state of a uniform transverse field, and you interpolate from this beginning Hamiltonian HB to your problem Hamiltonian HP. And the idea in adiabatic optimization is that we need to look at the minimum spectral gap that occurs in this interpolation Hamiltonian as this adiabatic parameter S moves from 0 to 1. Okay, and the adiabatic theorem guarantees that we can prepare the ground state of HP in a time that scales polynomially in the number of qubits and the inverse spectral gap, the inverse minimum spectral gap that occurs along the adiabatic evolution. Now, quantum annealing is kind of a broad term. People define it in various ways, but generally speaking, it's like adiabatic optimization, including more realistic effects. And in my talk, we use it to mean that we're sampling a low temperature Gibbs state, so it's near the ground state, but it is still a thermal state. And again, this represents the fact that quantum systems are going to inevitably enact with some environment. So what is this example that gives an exponential separation between quantum annealing and simulated annealing? It's called the spike cost function, and it's a bit symmetric cost function with a large energy barrier that creates a local minimum. Okay, so it's defined on the space of strings, but it's bit symmetric, so it only looks at the Hamming weight of the string. And so what happens if you imagine how classical simulated annealing behaves on this problem? Initially, you're at very high temperature, so you have a string centered around Hamming weight n/2, and as you cool the temperature down, the system moves closer and closer, but then it reaches this barrier. And this barrier has polynomial height and polynomial width, so it actually is going to take a very long time to climb over the barrier thermally, right? So it takes 2 to the So n to the a is the height of the barrier, and it takes at least time 2 to the n to the a to solve with simulated annealing, but Reichardt showed that quantum annealing succeeds in linear time or less when the height and width exponent together add to less than a half. Okay, so that's good news for quantum annealing, but maybe some bad news is that the traditional quantum annealing Hamiltonians that are the most well studied have a property called being stochastic. So stochastic Hamiltonians can be defined as having real and non-positive matrix entries, and this means that they can be scaled to substochastic matrices. Now, of course, this is defined relative to a particular basis, which for us is the computational basis. So a major result is that adiabatic computation with frustration-free stochastic Hamiltonians can be classically simulated in polynomial time. This is an awesome result, but unfortunately, the types of stochastic Hamiltonians that are of most interest in quantum annealing are not frustration-free along the adiabatic path. Another complexity result is that the stochastic local Hamiltonian problem is in the class AM, whereas we know that the fully general local Hamiltonian problem is QMA complete. So a major open question is, can stochastic quantum annealing be classically simulated in time that scales polynomially in n and the inverse spectral gap? Because this is the runtime of the quantum system to within a polynomial factor. Okay? And another reason to look at classical simulations is that implementing non-stochastic quantum annealing is very experimentally challenging, right? So we want to understand, we want to have as much motivation as possible to do that. Okay? So the idea of simulated quantum annealing, very briefly, is that if you look at a thermal state path integral for a stochastic Hamiltonian, right? So normally in path integrals, you have a sum over all paths, all trajectories that the system takes through some basis, and they get a complex amplitude assigned to each trajectory. But what's special about stochastic Hamiltonians, or one thing special about them, is that each of these trajectories is assigned a positive amplitude. So we can treat these positive amplitudes in the path integral as a probability density. And so if we normalize it, we get a legitimate probability distribution. So what you see here is an n by L grid, right? So the basis states of our system are n-bit strings, but now we're looking at length L sequences of n-bit strings. And everywhere you see a red line, you actually get a bit flip from a past string to a future string. So indeed, these states now of this probability distribution look like paths in the basis of the quantum system. Now, so simulated quantum annealing is the idea to discretize the adiabatic path and to sample from this distribution at each point using a Markov chain. The samples can then be used for Monte Carlo estimation of observables the same way that you use the path integral to estimate observables. Just to give a very rough idea of how this stationary distribution behaves, it's going to penalize configurations for the proportion of time along the path that they spend on bit strings with a high value of the cost function. And it's also going to penalize states that take a lot of jumps. So you could think of this as a kinetic energy and a potential energy. So our result is that simulated quantum annealing for the spike problem converges in polynomial time. So specifically, this Markov chain is going to equilibrate in polynomial time and find the minimum of the spike cost function in the same range that Reichardt analyzed, where a plus b is less than 1/2. Okay, and so specifically we prove this O tilde n to the 17th runtime for single site metropolis updates, where you randomly select a site in this grid and flip it. And in practice, everyone looks at what are called worldline heat bath updates, where you essentially are updating the entire past and future of a single qubit at once. So this gets an improved polynomial scaling of the runtime. Okay, so to visualize how the system behaves, initially when the adiabatic parameter is near 0, so this is a projection of that grid we just saw onto the Hamming weight space. So when the adiabatic parameter is near 0, the trajectory is centered around n over 2. And as the adiabatic parameter increases, the trajectory approaches the location of the spike. And at some critical value, what you have is some of the bit strings in your path are above the spike, and some of the bit strings are below the spike. But the key is that they don't all have to step on the spike at once, right? So they can sort of slip through one at a time. And once you're across the spike in the lower right, then you're basically home free to find the global minimum. Okay, so some of the ideas in our proof, well, the big idea is to compare the simulated quantum annealing Markov chain with and without the spike term. Without the spike term, it's a very simple system because the bits are non-interacting. Okay, so for worst case distribution, for worst case configurations, these two distributions might look very different. But what we show using expectation values of the quantum system is that for typical configurations, these two stationary distributions don't look too different in this regime where a plus b is less than a half. Okay, so in terms of the Markov chain analysis, we write down canonical paths for the system without the spike and use these to construct canonical paths for the system with the spike within this typical subset where the distributions don't look too different. And then we have to argue that leaks outside of this subset are rare. Okay, so what we really get is a quasi-equilibration of simulated quantum annealing within a subset of the state space, and then we use the adiabatic path to guarantee warm starts in this subset. Okay, so to illustrate this idea, we have, so it's really a comparison of Markov chains where we use most of the canonical paths for the spikeless system to build canonical paths for the system with the spike that have the same congestion, but only within this subset omega g of good states. And then we prove that omega g has a large measure. So what you can see here are in the yellow region, that's meant to signify omega g, and these arrows indicate paths between states of the Markov chain. Now, when we add in the spike, we now have these bad regions, these omega b regions that are like punctures in our state space. And some of the canonical paths we had before might pass through these punctures. But the idea is that we can sort of use this transitive property to build new paths that don't encounter these punctures, so they only stay within the good subset. Okay? All right, so we've shown that simulated quantum annealing can inherit some of the quantum advantages of quantum annealing on quantum hardware. And we've given the first proof of an exponential separation in the asymptotic performance of classical simulated annealing and this quantum-inspired classical algorithm called simulated quantum annealing. So one idea is, can we apply the ideas in the proof to better understand the stationary distribution and convergence properties of simulated quantum annealing more generally? Remember, the whole idea of a Markov chain is that you start at an initial point and converge to a distribution. You forget where you came from. But somehow we know from practical simulations that in simulated quantum annealing, the warm starts you get from the adiabatic path are very important. And so our proof kind of captures this aspect because it's a quasi-equilibration within a certain subset of the state space that captures all of the relevant information for estimating quantum observables. Okay, so besides path integral simulated quantum annealing, there are other quantum Monte Carlo methods for simulating stochastic Hamiltonians. However, we know that there are good reasons why none of the existing quantum Monte Carlo methods can simulate stochastic quantum annealing in full generality. So if you're interested in this grand conjecture of simulating stochastic adiabatic optimization, and you want to do it using a Markov chain Monte Carlo method, well, you have to invent something new, some new variant that no one has described before. Okay? Thank you very much.
Are there questions for Elizabeth?
I'll just let this animation of the system run while we take questions if there are any.
Well, let me get us started then. So I believe that people have constructed other toy problems where you have more than one barrier, and they're supposed to model some kind of rugged energy landscape. Now, do you have an intuition? I know it's maybe a vague question, but is there some intuition for whether or not simulated quantum annealing should be able to handle that sort of problem?
Yeah, that's a good question. So our comparison method could potentially work more generally. And so the key is that when a plus b is less than a half, the quantum system itself has a constant spectral gap. And so what really happened is that the presence of the spike hasn't deformed the wave function too much, right? And so if you have more of these spikes of modest size, and they don't necessarily deform your wave function too badly, then yeah, you might be able to apply some of these methods.
Thanks.
Hi. So I'm wondering, have you tried the other classical optimization algorithm for this particular problem?
So there are some other classical optimization algorithms. Like a popular one is spin vector Monte Carlo. Okay, but some of the drawbacks of these other ones is they're slightly ad hoc. So a very nice thing about simulated quantum annealing is it's really trying to fully capture the path integral of the quantum system, and so it's not just so spin vector Monte Carlo, for example, only looks at product states. And so it won't capture the full physics, whereas simulated quantum annealing with the path integral method potentially preserves all the entanglement and all the features in the quantum system. So that's why we felt that this was the best algorithm to target, because it faithfully captures the quantum system in more complicated examples. Right?
Okay, thank you.
We have time for a couple more questions, if there are any. Okay, let's thank Elizabeth for a nice talk. Okay, so our next speaker is Michael Jarret from Perimeter Institute, and he will continue the discussion of quantum Monte Carlo methods applied to stochastic Hamiltonians.
Oops. Okay, great. First of all, can everyone in the back hear me? Just give me a thumbs up if I'm good. All right. Yeah. Is this any better? Yeah? Okay, great. So I'm going to be talking about kind of a different classical paradigm you might want to think about contrasting adiabatic optimization with. And it's diffusion Monte Carlo, and for whatever the reason, this has been understudied to date. And you're not, okay, 1 second. Is that, yeah? I can also just try and speak louder if that helps. Okay, so we are going to take a look at diffusion Monte Carlo and contrast this with adiabatic optimization as an alternative paradigm within which you might want to study the adiabatic optimization algorithm. And this is some work that I did in collaboration with Stephen Jordan and Brad Lackey while I was at Quix. Okay, so why do we want to talk about diffusion Monte Carlo? Well, one is there's been a lot of analyses so far in path integral quantum Monte Carlo, and it's nice to do something different. But diffusive processes, because they're just heat diffusion, you can also prove an adiabatic theorem, which I'm not going to, for reasons of time constraints, not going to do today. Now, these path integral methods, as Elizabeth just mentioned, have these topological, or not specifically these, but she just mentioned they have obstructions. In particular, they have these topological obstructions. But when we're doing this diffusive process, at least in the way that we're going to be construing it shortly, we shouldn't be subject to feeling these sort of topological constructions, because we're not going to be constructing these kind of path integral world lines that are going to get stuck in places. So real quickly, Elizabeth did a really great introduction, so I'm just going to refresh our memory on what a stochastic Hamiltonian is. And it's going to be any Hamiltonian that can be expressed as, where is that? I can't see my pointer. It's going to be any Hamiltonian that can be expressed as some sort of sum between a combinatorial Laplacian, and that could also be a normalized Laplacian, just a Laplacian, and some other diagonal matrix. And we're going to pretend that this is positive semi-definite at the moment. Doesn't really matter. And that diagonal matrix is going to be our cost function. So that's going to be, when we're doing the algorithm, what we're actually looking to optimize. Now, all this is really saying is that the off-diagonal terms of the matrix should be non-positive. Okay, so quantum adiabatic optimization is going to be this sort of interpolation where we're going to vary between the Laplacian, which has a known ground state, and into this cost function, which we're searching for the ground state of. And the adiabatic theorem tells us that if we do this slowly enough, we should end up in the ground, we should stay in the ground state pretty much the whole way. Now, one of the real reasons that we're going to be studying these stochastic Hamiltonians as diffusive processes is that these serve as the infinitesimal generators of substochastic processes. And you get this just by throwing it into that expression right there. So, So here's a really simple example. All right, on the left in the top line, you've got the graph Laplacian for a barbell graph, just two vertices that are connected by an edge. And the top right term is just some matrix where the cost function is 1 if you're in the upper left vertex and 0 if you're in the lower right vertex. So this is probably the most straightforward example you can look at. And now we're going to pretend that delta t, this really small time step, can be taken to be a half. And you see when you just throw it into expression, what you get is some matrix where the row sum is everywhere less than or equal to 1, and also everywhere, every term is greater than or equal to 0. All right, so the ground state distribution of the top Hamiltonian is quite clearly going to be an eigenvector, in this case the highest eigenvector of the bottom Hamiltonian. Now, this is great, except if we want to apply this as a random walk or as a Markov chain, you're going to notice that applying the bottom line is going to reduce the norm of your vector, right? So you're just going to get a decay in the norm, and effectively, as heat does, it dissipates. Okay, so what do? Well, basically, we're just going to take Schrodinger's equation, and we're going to consider it an imaginary time. I prefer to just think of it as just considering the equivalent heat diffusion, but if you like imaginary time, you can. And then we need to get rid of somehow this decay of the vector. So we do this by adding in nonlinearity. Oh, my computer just went nuts. All right, so we do this by adding in some nonlinearity. And what this expected value term of the cost function is basically telling us that we're going to throw back in whatever dies off and add back to the one norm of our distribution. Okay, so this is, if you can convince yourself that this is going to preserve it. And then we're going to do things by this lower line here, which is just the first order, the first order expansion in delta t. Okay, so we want to approximate that somehow, and we call this method Substochastic Monte Carlo. And I don't know why this isn't going. Okay, so first thing, obviously a random walker, and for those of you who don't know, this is Randy, is going to walk by the adjacency matrix terms of the graph Laplacian. So that just gives us an assignment of values for the probability of walking. Then the second thing you can do, Randy can die. And so Randy can die specifically if his potential is above the average potential of the cost function for the walkers that you're seeing. And then his potential might be below the average potential for the cost function you're seeing, in which case he can spawn and give birth to a new walker. This is just what I mean by a walker coming from infinity back to the site X currently occupied by Randy. And the last possible option is that he just does nothing. And so this is just whatever probability remains. And this is going to have some stuff similar to this go with the winner's algorithm of Aldous and Vazirani. They have some interesting differences, but you know, they really match up pretty well in a good regime, and you know, it's kind of nice. So let's, in the interest of time, just see how this works out. Oh, sorry, yeah. So we're going to use this to optimize some function. So you know, we're going to vary a of t here. So originally there's going to be a lot of dynamics, and at the end of the day there's going to be no more dynamics and a bunch of statics just killing in birth. Okay, so this is what it looks like. We're currently interpolating between the dynamics and the statics, and you can see that the distribution is basically behaving like the ground state and drifting left. So this is kind of that Hamming ramp that Elizabeth was just talking about. And we can also throw a spike in there, just like the prior talk, and you'll see that it gets hung up for a second, and then as soon as anything goes over, the rest of the distribution is going to just teleport across the spike. And again, this is because of that birth-death process. And then I did this with an exponentially large spike just to show it, but we don't have time, so let's skip it. All right, I can come back if anyone's interested later. So here's a conjecture you might have. Hey, you know, this worked pretty well. We got through that spike. So if we have a decently sized gap, you know, and our adiabatic optimization algorithm is reliably picking out the optimal state of the cost function, is it the same case for substochastic Monte Carlo? And, you know, That would, of course, be too good to be true. So here's a particular Hamiltonian, same sort of Hamming ramp cost function, right? The potential is just whatever the Hamming weight of the particular vector you're currently at is. We choose b, this parameter, to just be that because that's what works. And we interpolate between 0 and 1. And you find that if your quantum state, the probability given to you by the ending quantum state for the all zeros vector is a constant, you have an exponentially small probability given to you by the quasi-stationary distribution. So if you believe that your distribution is actually the quasi-stationary distribution, then right here you've already got a divergence that's exponential. Now, if you're paying attention, you might say, Mike, wait a second. That's not what we were looking for. What we really wanted to know is, are we really close? We have the wrong norm, but are we really close to the actual vector that is the current eigenstate? And so we're going to tweak that prior example in order to actually show an obstruction to that. So, great. So, all we do is we add on this term, which is just some parameter times the projector, and now we're going to interpolate slightly on that Hamming ramp, get to a point where there's a little bit of our distribution, just enough, pull down that site, pulling in some more accumulation, and you'll find that this is even the projected quasi-stationary distribution amplitude for the all zeros vector of the actual substochastic process. And we're going to miss this because that site at the point where we started pulling down the all zeros vector had an exponentially small amplitude that we just saw. Okay, so if that's the case, what is this going to be good for? Well, it turns out that, okay, we can't do absolutely everything, but this actually winds up being a very good optimization algorithm. And I have more time than I thought I did. So we entered this in last year's max K-SAT competition. And these are the results. There's a bit of issues with scalings. You probably shouldn't see this, but like this weird shape here. It should probably be exponential because we actually programmed an exponential runtime into the thing. And it doesn't show. And that's probably just because of quirks with the evaluation environment. But anyway, you can see that SSMC here is pretty competitive with leading max SAT solvers. And this is pretty cool because, well, we didn't really intend to design a SAT solver. So at least in this regime of the problems that we were optimized over, we're doing pretty well. And not to hide anything, there are other problems that we did not do so well on. And we were really hoping to go back and fix that up this year, but there's no more competition. So if anybody wants to host it, let me know, and we'll definitely enter. Okay, so there we go. So what's the take-home message then? These population algorithms, like diffusion Monte Carlo style things, are going to suffer from these rare event sampling problems, right? You're going to get a rare event or certain events that when you sample them are going to really perturb your distribution, right? And so any of these population things that kind of sample these events and try to extrapolate the distribution are going to suffer from these sorts of L1, L2 divergence obstructions. But even still, SSMC winds up being an efficient optimization algorithm, so this is great. This is motivation for seeing how classical algorithms influenced by quantum algorithms are really going to change classical computing. And in many practical cases, we're actually going to simulate what the adiabatic algorithm would do rather well, but there are going to be instances where we're going to have trouble. And also, I hid this, but SSMC is going to be able to provide a nice mathematical framework for actually analyzing these things because we have a nice diffusion process that we can look at directly, analyze, at least in principle, with a lot of the same tools we're already using to analyze adiabatic algorithms. All right, so some open questions are pretty much everything. And I'm not going to list them right now, but I will go back and give you one. It's a challenge problem. This has been open for quite some time. Prove that this happens. So if anyone can prove that, I'd be thrilled. And I can leave it there and take questions.
Questions for Michael? Okay, so I have one.
Yep.
So people have done comparisons of simulated quantum annealing with, you know, this D-wave machine and with other, sorry, yes. People have done comparisons of this simulated quantum annealing, this classical algorithm like the one you described, and the D-wave machine and other classical algorithms. And have they done such a comparison with the diffusion Monte Carlo?
One person in the room has. We have not really. Well, are you talking about diffusion Monte Carlo like we did, or diffusion Monte Carlo?
Just more
like,
generally,
to the best of my knowledge, no. And it's probably because I think if I understand like what people do with standard diffusion Monte Carlo, it's not really that easy to adapt. You really need to come up with something more along the lines of what we did here. But we've run some comparisons locally of our algorithm against some of the D-wave examples.
But I guess like the reason I ask is because it seems like what you showed is that it seems to be a competitive algorithm for MaxSat.
Yeah.
So do you have a sense of whether it's more competitive than Worldline Quantum Monte Carlo?
On MaxSat. I would hypothesize that it is, but I wouldn't want to commit to that. So what we've seen in the past is that we get kind of the same scaling as Worldline Quantum Monte Carlo, but we kind of can bring down the overhead some. But that's on low, you know, sort of qubit examples, so it's really hard to say. I've never tried Worldline Quantum Monte Carlo on MaxSat. It would probably be something for somebody to give a shot to.
Thanks. Other questions? Okay, so let's thank Michael again.